free body force diagrams. So they're pretty much exactly what it says. When we say free body, we're talking about an object that's by itself, free of anything else. In this first case, I have a book sitting at rest on a table. We're most interested in the book. We don't care about the table. So we're not going to draw the table. Just draw the book. Just draw one thing at a time. So here I have a book, that rectangle. It's a book sitting on a table. Forget the table. Now we're going to draw a force diagram, and we'll represent forces with vector arrows because force is a vector. And we'll talk more about that later on. But okay, so here's what we do. There's a book sitting on a table. What forces are acting on the book? Well, gravity. If you're on Earth, gravity is always acting. Or on any planet, you have gravity acting on you. It's always straight down. So this arrow right here would represent, or can represent, the force of gravity. So F for force, the force of gravity. The force of gravity pulling down on a book. That's the only force, as far as material objects for now, that will be an active force no matter whether you're touching the earth or not. Like a ball in the air will also have a force of gravity even while it's in the air, even though it's not touching the earth. Every other force you draw on these diagrams will be because it's touching something. Whatever the book is touching, there'll be a force. Or anything that touches the book will exert a force on it. So anything that touches will exert a force. The book is touching the table. The table is actually supporting the book with an upward force. I'm going to call that the force of the table. And for now, we're going to draw them the same length because they are, if the book is sitting at rest, those two forces are the same size, different direction. They'd be measured in newtons, like maybe 10 newtons down and 10 newtons up. We'll talk about that later on, but right now I just want you to get used to drawing the diagrams. So we have F sub gravity, force of gravity, and F sub table, force of table on the book. Now what if the book is being pushed across the table? Once again, I'm going to draw the book as a rectangle. The book is sitting on a table. Actually, it's not just sitting there now, it's being pushed. But while it's being pushed, the force of gravity is still active on the book. So we still have the force of gravity pulling down on a book, and the force of the table supporting the book, keeping it from falling, support force, force of table, the same as it was in the first part. But now we're pushing it. It doesn't really matter who or what is pushing it, but something is pushing the book. I'm going to push an arrow, put an arrow on there. That's the force of the push or the pushers. Now in some literature, when teachers, professors draw these free body force diagrams, they always put the tail of the vector in the middle of the object. I don't always do that, but you might see that in some scenarios. The most important thing, however, is that the arrows point in a given direction. Some vectors are going to point up, some down, some left, some right. It's not so much where you put the tail or where you put the head or where you put the actual vector, but make sure it's touching, quote-unquote, the object, the book in this case, and it has an arrow in the right direction. Third situation here, a book on a table with friction. So now, same scenario as before, except for now there's friction. So here I have a book. We still have the force of gravity straight down. And I added the other forces, the force of the table up, the force of the push, trying to push the book forward, and now I'll add the force of friction, which always opposes your motion. So here we have the force of friction, force of friction. Now the force of friction may be equal to, less than, or greater than the force of your push, and we'll talk more about what that means later on. But these would be free body force diagrams in these particular scenarios. Let's do some other ones. So in the first case here we have a ball falling in the air, falling straight down because of the force of gravity. The force of gravity is the only thing acting on the ball. So there's the first diagram, free body force diagram for the baseball, or any kind of ball, or any kind of object falling because of gravity. In the middle case here, we have a ball falling straight down, and there's air resistance. So here's the first diagram I have there in the middle is one scenario, force of gravity still pulling the ball down, and the force of air opposing the motion. It's a frictional force, so force of air resistance is up. Here's another possible answer though. So the second part of this middle diagram is another possible answer. You don't have to do both of these diagrams for the free body force diagram. So now the second diagram there in the middle is equivalent to the first diagram. You have the force of gravity down and the force of air resistance up. And they may or may not be equal to each other. The force of air resistance can be greater than, less than, or equal to the force of gravity, and we'll talk about those circumstances later on. Now the third diagram. Alright, in the third diagram, the ball is traveling upward. The force of air resistance opposes the direction the ball is moving, so it's in the same direction as the force of gravity. Once again, it may or may not be equal to the size or the magnitude of the force of gravity, but they're both in the same direction. And again, in this last scenario here, there's another possible way to draw the diagram like such. So this last diagram on the far right is equivalent to the one next to it. Same diagram. You don't need to do two diagrams like that each time. I'm just giving you an option. Force of gravity is down, the force of air is down. They're both pointing down and restricting the motion of the ball. Let's go to another example. Alright, so now we have a person in an elevator. Once again, it's a free body force diagram. We're not drawing the elevator. Forget the elevator. It's the person we're worried about. You'll see a common theme here. Now I'm using blue, but you can use any color you want, including red. But force of gravity. It's been a similar arrow in all the diagrams I've drawn, because if you're on Earth, you always have the force of gravity pulling down on you. Technically, I can make this force of gravity a lot longer because it's a bigger force on a person than it is on a ball. But right now, the direction is the most important thing here. Now, if you're in an elevator, the only thing you got to worry about is what's touching you. And there's something touching your feet, essentially, if you're not leaning against a wall. It's the floor of the elevator. And that exerts a force on you in the upward direction. So I draw that in. Force of elevator. Or you could say the force of the floor. Either one would be okay. And once again, it may or may not be equal to the force of gravity. It could be greater than, less than, or equal to it. But what about if the elevator is going down? Force of gravity is, once again, still straight down. Another thing to note is that keep your diagrams as simple as possible. We're drawing a person. What you'll see me do in a few minutes here is I'm going to draw a person as a box, or as a square, or as you could draw a person as a ball. Keep the diagram simple. In fact, the more complicated you make your person or your dog or your ball, whatever it is, the more time you're sort of wasting. If you like to draw pictures, go ahead, but keep your diagram simple. We're drawing a person here, and the force is acting on the person. So gravity will always be acting, and then whatever's touching you will act and create a force on you. In this case, the elevator is going down. However, it looks the same as the previous diagram. The force is from the floor, or the elevator, is still pushing you up. Force of elevator. Now that's going to be tricky to explain later on, but hold that thought for now. If you're standing on a floor, the floor is always holding you up, exerting an upward force on you. Gravity is always down. So these two diagrams look the same whether you're going up or down. And once again, we'll talk more about that later on. But let's try another one. Okay, I'm going to simplify this. This square represents the fireman. We don't care about the pole. We don't care about the shape of the fireman. All we care about is that there's a fireman. You can draw as a round ball or a box or a square. But what are the forces? The arrows are the most important thing. And once again, we have the force of gravity. But what other forces are acting on the fireman as he slides down the pole? Well, is he touching the pole? And he is, or she. So there's a force. Which way is the force acting on the fireman as he or she slides down the pole? And in this case, it will be up. And it can be a force greater than or less than or equal to the force of gravity. Force of the pole acting on the fireman. You cannot technically exert a force on yourself. It's got to be some outside object exerting the force on you. The force of gravity is a force from the earth exerted on you. The force of the pole or the force of the floor, like in the previous problems, or the force of air. Something outside yourself exerts the force on you or the object. Alright, what if you're climbing up the pole? Again, force of gravity is downward, excuse me, just like in every scenario we've had. But what is the direction of the pole's force on the fireman as you climb the pole? You are not exerting the force on yourself. You're exerting a force, or the fireman's exerting a force on the pole. But what is the pole doing to the fireman? Exerting an upward force, just like in the previous case. Force of the pole. So there we have a free body force diagram. Many examples. Here's one more variation of this last diagram. These last two diagrams on the right are the same as each other. Doesn't really matter where you put the up arrow at, but it's an up arrow. And the force of gravity is still straight down. So those last two diagrams there are equivalent. Free body force diagrams.